So we will be deriving the Gibbs distribution by an alternative method known as the method of most probable distribution. So let's see how to do this one. So here we consider our system to be a member of a grand canonical ensemble. So let's consider a grand canonical ensemble. So that is where we start with. Consider a grand canonical ensemble. I'm abbreviating it as GCE of n identical systems which are in different microstates but sharing the same macrostate, say mu vt, having macrostate mu vt, which are labeled as, the systems are labeled as, for easy reference, 1, 2, 3, etc. up to curly letter n, mutually sharing a total number of sharing. So all these systems put together are sharing a total number of, so these are some basic assumptions, total number of n bar into n number of particles, and e bar into n value of energy. I think I can understand what is this n bar and e bar, where n bar and e bar are the average energy per system of the particle and average number of particles in the system. So we can see that they are the average values of n and e. Please note the difference in the notations here. The script letter or curly letter n denotes the number of systems in the grand canonical ensemble, each of which is consisting of certain number of particles, and the particle number is permitted to change in a grand canonical ensemble. Okay, so since the particle number is permitted to change in a grand canonical ensemble, that is why in place of n we are taking n bar. Okay, and also the energy of a system in grand canonical ensemble is also permitted to vary. Hence, average energy E bar is used, and when E bar and n bar are multiplied with the script letter n, which is the number of systems, we get the total number of particles in the ensemble. Okay, remember, it is the total number of particles in the ensemble, and the n bar and e bar are the average values of n and e in a system or per system in a system. Okay, and since it is fluctuating, we are taking average values. So that's the thing. Now, or if you just write, that is n bar is nothing but average value of n in the system, and e bar in our expression is equal to the average value of energy in the system, okay, or of the system. Now let's introduce another symbol. Let n, small n, subscript r comma s be the number of systems in the ensemble having nr particles and es energy at any time t. Okay, so let nrs denote number of systems. These are the number of systems in the ensemble, in the grand canonical ensemble, having nr number of particle and energy Es at any instant t. So we can say that if you add up all nrs values for all possible values of r and s, you will be certainly getting the total number of systems in the grand canonical ensemble. That is, we can write the conditions here. Sum over all R and S values, all possible RS values, sum over n RS should give you the total number of systems in the ensemble, which is script letter n. We call it as equation number 1. Same way, you can understand that sum over RS, all possible values of R and S, NRS, you multiply NRS with what? NR. NRS into NR will give you what? The total number of particles in the system, total number of particles in the ensemble, not system, in the ensemble, which is nothing but we have denoted this n, script letter n into n bar. So that is equation number 2. The same manner, I can write one more relation for the total energy in the ensemble, that is sum over all RS values, multiply NRS with what? ES. Energy is ES. So the number of systems having ES energy is NRS. So you multiply the number of systems with what? The energy ES. So you'll be getting the total number of systems having that particular energy. Okay, so NRS ES will be equal to what? So the script letter En, which is the total number of total number of systems in the ensemble into what? Of course, you know that will be into average value of energy. So these are the 3 constrained equations that is satisfied by the systems in grand canonical ensemble. So the similar type of a constraint equation we had written in the beginning of what you call canonical ensemble also, where the second constraint was absent. Okay, you can see that only the constraint was NR ER is equal to N into E bar, and sum over NR was equal to En. So please refer back to the constraints that we have written in the case of canonical ensemble derivation. You will see that the equation number 2 here, the constraint given as equation 2 here is an additional constraint which arises out of the what you call the variation in the number of particles in the system. ഇപ്പോൾ നമുക്കറിയാം ഇവിടെ എന്താണ് ഗ്രാൻഡ് കനോണിക്കൽ എൻസംബിളിൽ നമ്പർ ഓഫ് പാർട്ടിക്കിൾസും എനർജിയും രണ്ടും വേരി ചെയ്യാൻ പെർമിറ്റ് ചെയ്യുന്നുണ്ട്. അതുകൊണ്ടാണ് ഇവിടെ നമുക്ക് 2 കൺസ്ട്രെയിൻറ്റുകളും കൂടെ ഒരുമിച്ച് കൊണ്ടുവരേണ്ടി വരുന്നത് എന്നുള്ള കാര്യം മനസ്സിലാക്കുന്നത് നന്നായിരിക്കും. So that's the thing. Now what we are going to do, the method is the method of most probable distribution. So we have to calculate, we have to determine statistically which will be the most probable distribution. So out of a lot of distributions of energy and number among the systems, ഈ സിസ്റ്റങ്ങളുടെ ഇടയ്ക്ക് നമ്പറിലും എനർജിയിലും ധാരാളം വിതരണക്രമങ്ങൾ അല്ലെ ഡിസ്ട്രിബ്യൂഷൻസ് പോസിബിൾ ആണ്. അതിൽ ഏത് ഡിസ്ട്രിബ്യൂഷൻ ആയിരിക്കും ഏറ്റവും പ്രൊബബിൾ എന്നാണ് നമ്മൾ ലഗ്രാഞ്ചസ് അൺഡിറ്റർമിൻഡ് മെത്തേഡ് ഓഫ് മൾട്ടിപ്ലയേഴ്സ് വെച്ചിട്ട് കണ്ടുപിടിക്കുന്നത്. സോ വി ക്യാൻ ജസ്റ്റ് ഡിഫൈൻ എ സെറ്റ്. സോ എനി സെറ്റ് n, I'm writing the set n, set of all n values, okay, set of all n values of numbers nrs, any set nrs of numbers nrs which satisfies the conditions 1 to 3, which satisfies the conditions or which follows the constraints or conditions. Constraints are nothing but limiting conditions. Conditions 1 to 3 is one of the possible distributions of energy and number. Is one of the possible distributions out of many possible distribution. Any distribution which obeys what is that? The equation number 1 to 3 is a possible distribution of energy and number among the members of the ensemble. Now, see, by using the combinatorics, or we can say by using the idea of permutations and combination, we can say the number of ways of realizing such a distribution. Therefore, number of ways of realizing or obtaining such a distribution, number of ways of realizing such a distribution is given by W, the weight factor W, corresponding to NRS. In order to denote that it is a W corresponding to the set NRS, satisfying equation 1 to 3, I am writing W of NRS is equal to the, what is the total number of ensemble, total number of systems in the ensemble? That is script letter n. So that is n factorial. We have done a similar calculation in the case of canonical ensemble distribution also, divided by pi r comma s. So in the bottom I am writing pi r s nrs factorial, n r comma s factorial. So see that these subscripts are just to denote all possible values of r and s. So what I have written here is note this particular notation. See, I have written in the denominator as pi of pi over all values of r and s n r comma s factorial. So maybe okay, I think you are familiar with that symbolic notation of pi over some quantity. So you know that in notations, sigma over say sigma over n or any number, say sigma over r, nr denotes what? N1, it is a summation, n1 plus n2 plus etc. up to say some value of r, say nr. Similarly, since sigma stands for summation, pi in such equations stand for multiplication. So pi over say something like r, pi over r means it denotes pi over r nr. If somebody writes pi over r nr, it denotes n1 multiplied by n2 multiplied by n3 likewise up to some value of r. So pi over something means multiplication, like sigma over something denotes what? Addition. Okay, so here pi over two of the indices are there, r and s. So for all possible values of r and s, we have to multiply the values of nrs and its factorial. So it is just like nrs factorial. It is like n1 okay, see something n11 factorial, n12 factorial, n13 factorial. Likewise, you can just go on changing the values of r and s. Okay, so you have to just multiply, go on multiplying each of the terms, right? So where pi rs stands for the product of nrs for various values of r and s. So let me call this equation as equation number 4. Now already we have explained from where do we get such an expression. So this equation number 4 actually represents the number of permutations of n things taken all at a time, of which say p are alike, q others are alike, r others are alike, etc. Then w will be given by, see you have got say that if you have got n things total, so this is an example. So n total things are there, and out of n, p of them are similar, q of them are identical, and r of them are identical, like that. Then how many permutations? How many permutations are possible taking n? Okay, means all at a time is given by w is equal to, this is an expression from permutation theory, n factorial, the total number factorial divided by, then you have to take as bunches, p factorial into q factorial into r factorial. Likewise, it goes on, where the only condition is that p plus q plus r should be equal to n. Okay, so I had explained this one by taking some example of some fruits, like okay, so there are some n oranges, okay, see or p oranges, q apples, and r grapes. Then how do we, or okay, you can take that 3 colors of things are there. So how do we make the permutation? That is given by this one. So you can see here in expression number 4, in place of small n, okay, we have got a script letter n number of systems in the ensemble. Okay, and sum over r nrs, sum over nrs is equal to n. So the denominator is also following the same rule that we have discussed here. So just see that these notations are from permutation theory that we are taking. Now proceeding on to the next. So we got what is the number of distributions. Now you know our aim is to find the most probable distribution, for which we have to find out, or we have to maximize this particular w. Okay, so in order to maximize w, let's initially take log of W. As I told you, W is the number of permutations, which will be very large in the case of large number of systems. So here also what you have to do, you have to take logarithm of that number, and then we will be just what? Maximizing. So taking logarithm of that equation, so taking logarithm, I'm just proceeding, taking log on both sides, so it will be equal to log of W, that will be equal to log of n factorial, script letter n factorial, minus, okay, you know that it will be log A minus log B, okay, then it will become, product will become, when you take log, product will become what? Summation. So instead of pi rs, I am writing sigma rs, so log of n rs factorial. So hope you can understand that, because we had W is equal to n factorial divided by pi over rs n rs factorial. Okay, so it is just like something like, okay, see, denominator is a product. And you know that when you take log of a product, for example, log of A into B, okay, A into B into C, like whatever it is, log of a product is nothing but a, what is that? The sum of the log, that is log A plus what? Log B. So I can say log of product means I'm writing pi. Okay, pi of A and B. You can say A comma B. If I am writing it like this, then that will be equal to sum over, okay, you know, all the same quantities, that A and B. So log of the product will be equal to, what is that? Log of, so you can just see that sum over log of that quantity A and B. So that is why here you can see that when you take the log of LHS W, you will be getting log A minus log B, and log of the product is written as what? The sum of the logs. So that is why minus sum over rs, it is pi is now replaced with what? The summation. I think it's clearly understood. Now you know that in all these cases where the number of systems are so large, n is very large, so I can use Stirling's approximation, that n log n minus n. So this one will be, first factor will be n log n minus n, then minus, okay, sum over rs. Okay, I can write once again, I can apply the, what do you call, Stirling's approximation. So it will be nrs log nrs, then minus term, it will be becoming plus because of the minus that is there already outside. So I'm not using any brackets and all. So sum over rs nrs. Now you know what is going to happen. Similar steps have been repeated in the case of canonical ensemble derivation by most probable distribution method. So sum over rs nrs by equation number 1 is nothing but en. So these two things will be getting cancelled. So what we are left with is n log n minus sum over r comma s n r comma s n log n r s. So we call this one as equation number 5. Now we have to find out the most, this is just W denotes the number of ways of distributing energy and number amongst the members of the ensemble. Now we need the most probable distribution. So for the most probable distribution, W NRS will be a maximum. So W NRS will be a maximum, then log of W NRS also will be a maximum. When say X is a maximum, log of X also will be reaching a maximum, simple logic. So for most probable distribution, distribution of what? Both energy and number amongst the members of the ensemble. Okay, for most probable distribution set, let me denote the most probable distribution set by the symbol NRS star. Okay, so the star denotes that particular value of distribution set which makes W maximum. The number of ways of permuting will be made as what? Maximum. Now, let's take that this log of W will be a maximum. W will be a maximum. So it's the case of log of W will be a maximum. So log of W will be a maximum. So, but the condition is that means we have to maximize log of W given by equation number 5. But the condition is that while you maximize this log of W, that three constraint equations given by 1, 2 and 3 should be satisfied. അപ്പോൾ നമുക്ക് ഇവിടെ നോക്കേണ്ട കാര്യം ഇതാണ്, ഒരു ഫംഗ്ഷനെ മാക്സിമൈസ് ചെയ്യണം വിത്തിൻ ദ കൺസ്ട്രെയിൻസ്. ഓക്കെ, ഒരു നിബന്ധനകൾക്ക് വിധേയമായിക്കൊണ്ട് ഒരു ഫംഗ്ഷനെ മാക്സിമൈസ് ചെയ്യപ്പെടണം. അപ്പോൾ അങ്ങനെ ഏതെങ്കിലും ഒരു നിബന്ധനകൾക്ക് സെറ്റ് ഓഫ് കണ്ടീഷൻസിന് വിധേയമായിട്ട് ഒരു ഫംഗ്ഷനെ മാക്സിമൈസ് ചെയ്യേണ്ടി വരുമ്പോഴാണ് നമ്മൾ എന്താണ് ലഗ്രാഞ്ചസ് അൺഡിറ്റർമിൻഡ് മൾട്ടിപ്ലയേഴ്സ് മെത്തേഡ് ഉപയോഗിക്കുക. സോ വി യൂസ് ദ മെത്തേഡ് ഓഫ് Lagrange's undetermined multipliers whenever you have to maximize or extremize a given function which must obey a set of what? Constraints represented by some constraint equations. For നമ്മുടെ കേസിൽ, in our case, there are three constraint equations that is to be satisfied. Okay, so given by equation number 1, 2 and 3 here. ഓക്കെ, ഇപ്പോൾ ഈ 3 കൺസ്ട്രെയിൻറ്റ് കണ്ടീഷൻസും ഉൾപ്പെടുത്തിക്കൊണ്ട് നമ്മുടെ ലോഗ് ഡബ്ല്യുവിനെ മാക്സിമൈസ് ചെയ്യാണ് ചെയ്യേണ്ടത്. അതിനുവേണ്ടി ഫോർ ദാറ്റ് വാട്ട് വി ഡു ഇസ് ദാറ്റ് വി ഡിഫൈൻ എ ന്യൂ ഫംഗ്ഷൻ വിച്ച് ഇൻക്ലൂഡ്സ് ദ ഒറിജിനൽ ഫംഗ്ഷൻ ലോഗ് ഓഫ് ഡബ്ല്യു വിച്ച് ഇസ് ടു ബി മാക്സിമൈസ്ഡ്, ആൻഡ് ഓൾസോ വി വിൽ ഇൻക്ലൂഡ് ദ കണ്ടീഷൻസ്, ദ കൺസ്ട്രെയിൻസ് ദാറ്റ് ഹാസ് ടു ബി satisfied in that function. So we define a new function. So for this okay, this only for our idea, we use the Lagranges method. So this is only for you to understand. You need not elaborate on Lagranges method. This is only for you to understand method of undetermined multipliers. Just okay, let's do it alpha, beta, gamma like that. We used in the earlier derivation alpha and beta. Here there are three constraints, so we will have to use three undetermined multipliers. Okay, so for this we will define. So for this we are defining a new function. I'm naming that function as f. Similar thing we have done in canonical ensemble also. You can refer back. Let f be equal to, so what will be f will be? F will be having the original function to be maximized, that is log w, minus I will be introducing 3 Lagranges multipliers. 3 Lagranges multipliers introduce ചെയ്യും, കാരണം 3 കൺസ്ട്രെയിൻറ്റുകളുണ്ട്. അപ്പോൾ ഈ മെത്തേഡിന് പ്രത്യേകത ഇതാണ്, എത്ര കൺസ്ട്രെയിൻറ്റ് ഇക്വേഷൻസ് ഉണ്ടോ അത്രത്തോളം അൺഡിറ്റർമിൻഡ് മൾട്ടിപ്ലയേഴ്സ് ഇൻക്ലൂഡ് ചെയ്യുക. 2 കൺസ്ട്രെയിൻറ്റ് ഇക്വേഷൻസ് ആയിരുന്നു കാനോണിക്കൽ എൻസംബിളിൽ ഉണ്ടായിരുന്നത്, അല്ലേ? നമ്പർ സം ഓവർ എൻ ആർ ഈസ് ഈക്വൽ ടു എൻ കിട്ടിയിരുന്നു, സം ഓവർ ആർ എൻ ആർ ഇ ആർ ഈസ് ഈക്വൽ ടു ഇ എന്ന് കിട്ടിയിരുന്നു. അപ്പോൾ അവിടെ 2 കൺസ്ട്രെയിൻറ്റ് ഇക്വേഷൻ ഉണ്ട്, 2 Lagrange's undetermined multiplier ഉപയോഗിച്ചത് ആൽഫ ബീറ്റ. ഇവിടെ നമുക്ക് 3 കൺസ്ട്രെയിൻറ്റ് ഇക്വേഷൻ ഉണ്ട്. സോ വി ആർ സപ്പോസ് ടു യൂസ് 3 Lagrange's undetermined multipliers which we are naming as alpha, beta and gamma. So I am beginning with gamma. Okay, so gamma times sum over rs, okay, nrs, sum over rs nrs, minus alpha times sum over rs nrs into nr, minus beta times sum over rs nrs into es. On a close look of this particular equation, you will see that first one, log w, is our original function which is to be maximized, given by equation number 5. Okay, so log w is the original function, and see, this factor is nothing but, you can see that is nothing but the LHS of equation number 1. LHS of equation number 1, which is the first constraint. And you will see that similarly the LHS of second constraint, sum over rs nrs nr, will be the coefficient of alpha in that equation, and sum over rs nrs es, LHS of equation number 3, the third constraint, will be the coefficient of beta. Okay, so you can see that this is from second constraint, and along with the beta you have got the third constraint. So this is the way in which you will be applying what is known as what? The Lagrange's undetermined. അപ്പോൾ നമുക്ക് കാണാൻ പറ്റുന്നുണ്ട് ഇക്വേഷൻ നമ്പർ 6ൽ നമ്മൾ ഒറിജിനൽ ഫംഗ്ഷനോടൊപ്പം തന്നെ എന്താണ് 3 കൺസ്ട്രെയിൻറ്റുകളെയും കൂടെ ആൽഫ, ബീറ്റ, ഗാമ എന്ന 3 അൺഡിറ്റർമിൻഡ് മൾട്ടിപ്ലയർ കൊണ്ട് മൾട്ടിപ്ലൈ ചെയ്തുകൊണ്ട് എന്താണ് ഉൾപ്പെടുത്തിയിട്ടുണ്ട്. അപ്പോൾ ഇനി എഫിനെ എക്സ്ട്രീമൈസ് ചെയ്യപ്പെടുമ്പോൾ ലോഗ് ഡബ്ല്യുവിനോടൊപ്പം ഈ കൺസ്ട്രെയിൻറ്റ് കണ്ടീഷൻസും കൂടെ ഒബേ ചെയ്യുന്നു എന്ന് ഉറപ്പാക്കാൻ വേണ്ടിയിട്ടാണ് നമ്മൾ ഈ കണ്ടീഷൻസ് ഒക്കെ ഇങ്ങനെ ഉൾപ്പെടുത്തുന്നത്. ഓക്കെ, സോ ദ ഐഡിയ ബിഹൈൻഡ് ഡൂയിങ് ദിസ് വൺ ഈസ് ടു ഇൻക്ലൂഡ് ദ കൺസ്ട്രെയിൻറ്റ് ഓൾസോ when our original function log w is getting extremized. That is our idea. Now our aim is to maximize this one. So for extremization, maximizing, we can say that the differential of that function f must be equal to 0. Okay, so you have to take differential of f, that is on LHS delta f equal to 0, or on RHS delta of, I have to take delta of that quantity. I can just write this one. So delta of, I am writing n log n. Okay, so for log w I am substituting equation number 5. So that is n log n minus sum over r comma s nrs log nrs, that is for log w I have substituted from equation number 5, minus all those things, minus gamma into sum over rs nrs minus alpha into sum over rs nrs into nr, nrs into nr, okay, nrs into nr, minus beta into sum over rs nrs into es. Okay, so that should be equal to 0. So you have to take delta of these things. Now see, before proceeding, you know n is total number of systems in the ensemble which is fixed. So n log n will be a constant. So taking the delta or differential, total differential of n log n, the first term will be equal to, will give you 0. So this one will give you, I'm writing it here itself so that we can just do that one. So that is equal to 0 minus, then what are the variables here? The variables here are nrs and you can see that yeah, here you will be getting only the variable as nrs and because nr and es both are what fixed for a given particular, what is that, you know, es is a given value that is fixed for a given system. This is unique. So here I'll write it's minus delta of sigma rs, second one sigma rs. So nrs is a variable, so it is of the product rule. First one is nrs, second one is log nrs, so I have to use the product rule. So let's see what I'm going to get, or better I will do it on the next page. That will be better because it's going to be a bit lengthy. So let me just take this quantity also to the next page. Yeah, so we have this quantity, this is what we have. So let's proceed with this one. Therefore first term will be giving you 0, so that is 0, first term, the delta of 0, that term is 0, minus it will be sum over rs. I am using product rule for the next quantity, that is delta of nrs times log of nrs, okay, first term udv, like that. Okay, then minus, so instead of plus a minus is there from common thing, sum over rs, then the differential of log nrs we have to write. So first I am multiplying with the nrs, the first term is nrs u into dv. So log nrs, what is the differential? That is 1 by nrs, 1 by nrs. Then I have to take function of function rule, that is what, delta of differential of nrs. So nrs, so that term is over, then minus gamma times, gamma is a constant, sum over rs, okay, delta of nrs, there is no issue there because only nrs is there, minus alpha into, then sum over, there also nr and es are okay, just fixed quantities there. So sum over rs minus alpha sum over rs, delta nrs into nr minus beta into, there also, okay, beta is a constant, so that is beta into sum over rs. Es is unique for a given system, so only the variable is nrs, okay, because we are trying to maximize nrs, right? So delta nrs into es, so we are treating, so that entire term should be equal to 0. Now you can just make some modification. This NRS and this NRS will be getting cancelled. So what is left there is delta NRS. You can see in all these terms that sum over RS is common and delta NRS is also common. So I am taking the summation as a common term minus, that is minus sum over RS. Okay, then what all things are remaining except delta NRS. So from the first term we will be getting the log of NRS. Since we have already maximized, since already we have applied the condition for maximization, now let us denote this NRS by NRS star. Already the maximization condition applied the about E condition satisfy in the NRS value that will be the most probable distribution set value. So I am denoting NRS star. So then here minus already taken outside, so what remains only 1. So plus 1. Then plus gamma, already minus is outside, and delta NRS is also, sum over RS delta NRS is also going to be outside. Okay, so plus 1 plus alpha NR plus beta, not minus, plus beta ES. Okay, all multiplied by delta NRS is equal to 0. We call that this is equation number some 7. Okay, now you know that in this expression this delta NRS is arbitrary. Okay, NRS എന്ന് പറയുന്നത് arbitrary ആയിട്ട് എടുത്തത്. So delta NRS is arbitrary. അപ്പോൾ ഇക്വേഷൻ നമ്പർ 7 സാറ്റിസ്ഫൈഡ് ആവണമെങ്കിൽ ഒന്നുകിൽ ഡെൽറ്റ NRS 0 ആവാം എല്ലാ കേസിലും, അല്ല എങ്കിൽ എന്താണ് the first term should be equal to 0. Okay, so for the summation to be 0 for any arbitrary value of delta NRS, we can say that the quantity in the bracket must be 0. Okay, so we can just say that that's a very, since delta NRS is arbitrary, means it is not okay, a special case or a specific case for 7 to be true. We can avoid all these okay things. See the integrand, or we can just say that okay, instead of integrand I can say that quantity in the bracket, the coefficient, okay, that should be equal to, invariably equal to 0 or identically 0. So which tells that log of NRS star, okay, so log of NRS star, I'm rewriting that one, that should be equal to, I'm taking all other terms to the other side. I'm putting it that quantity equal to 0 first, and then I'm taking all the terms to the other side. It will be minus of 1 plus gamma, minus of 1 plus gamma, minus alpha NR, minus beta ES. Okay, now you know that this gamma is a constant, 1 is also constant, so we can say that this is actually what is that, a set of constants, so which I can write as the logarithm of another constant. So I am writing minus 1 plus gamma as a logarithm of some other constant. Okay, log C, I'm calling it as log C for mathematical convenience, minus alpha NR minus beta ES. Okay, now so I can take log C to the other side, so it will be log NR star minus log C, which will become log A by B form. So therefore I can say log of NRS star divided by C, it will be equal to minus alpha NR minus beta ES. Got it? Okay, or what does it mean? It means that I can take NRS star, that will be equal, or that will be proportional to, at least, okay, that will be proportional to, okay, because C is there. So if you don't have C, then that is proportional to, I can say, e raised to, or exponential of e raised to minus alpha NR minus beta ES. So in as I have avoided the C, in that case I can say that that is proportional to. So let me call that this is equation number 8. Okay, now what we are going to do, you know, from equation number 1, or since sum over all RS values NRS is equal to N, the total number of systems in the ensemble, okay, I can say that the LHS, okay, you take, you can say NRS, what was that? NR star is proportional to e raised to minus alpha NR minus beta ES. So I can say that this N is proportional to sum over RS e raised to minus alpha NR minus beta ES. Okay, because that is NRS, that equation, right? So I'm taking just sum over RS to our previous equation. You can see our previous equation, I'm taking sum over rs on both the sides, so they should be proportional. Sum over rs, nrs will be proportional to n, the total number of systems in the ensemble. Therefore, let me call this equation as equation number some 9. Now I can divide equation number 8 by equation number 9. So similar steps were followed in our canonical ensemble formalism derivation also. You can just refer back. So that will give you equation 8 by 9 will give you nr star divided by total number of ensembles, total number of systems in the ensemble, that is n is equal to what happens, the proportionality constant will be c, that will be getting cancelled out. So that is minus e raised to alpha nr minus beta es divided by sum over rs e raised to minus alpha nr minus beta es. I think we are able to identify that this was nothing but the already familiar expression which we called as PRS in the earlier derivation. So this is nothing but the probability that our system at any given instant of time is found in a state with energy Es and number of particle Nr. So the LHS denotes, you can see that what is NR star denoting? That is in the most probable distribution case, NR star is the number of systems having energy Es and number of particle Nr out of total number of systems in the ensemble. So that is a ratio, that is a probability. And you know, sum over nr star will be equal to 1, that will be equal to n. So in that case, n by n will be equal to 1. So the maximum value of the probability will be equal to 1 as per equation or LHS of the equation also. So this is exactly the PRS, so which gives what you call the Gibbs distribution. So this is nothing but the Gibbs distribution. So you can see that we got the same expression for PRS by following the method of most probable distribution, right? So that is our aim. So we could just complete our derivation in that way. Now before we end the session, let's have an equation for average energy and average number. Okay, that would be helpful for us. So average energy, you know how to average in an ensemble formalism, and average number in grand canonical ensemble. So you know that in the case of canonical ensemble only we need to consider average energy because number is fixed. But in a grand canonical ensemble, both energy and number of particles are permitted to vary or fluctuate. I can use the word fluctuate. So we are supposed to define what is average energy and what is average number. So likewise, we can say that see average energy E bar, which is nothing but the ensemble average of E. It is given by definition of ensemble average sum over Rs PRS into ES. Hope you remember. Okay, average energy in the case of canonical ensemble was also defined like that was there sum over R PR ER. Okay, so where PR was the probability that the system is found in a state with energy ER. So here only difference is that there are two conditions. Instead of PR, it will be PR comma S. So summation also will be over R and S. And energy is not ER, it is ES as per the notation. So you can just substitute for this one. So this is equal to, from equation number, let me call this equation as equation number 10, which is our final equation. So substituting for PRS, this equation will become sum over RS. PRS I have to substitute, so I am writing ES first. ES into e raised to minus alpha NR minus beta ES. So what I am substituting is only a substituting equation but 10 here, whole divided by that denominator, that is sum over R comma S e raised to minus alpha NR minus beta ES. So that is giving you the average energy of a system in grand canonical ensemble. Same manner I can write N bar, which is the average number of particles in the ensemble, that is the ensemble average of N. By definition, that also can be written as sum over Rs PRS multiplied with NR. Okay, PRS multiplied with NR. In general, remember the ensemble average of any quantity, okay, it is given by sum over R F of R PR in a canonical ensemble, and this is equal to sum over Rs F of Rs PRS in the case of what? Grand canonical ensemble. That is a notation. So the same manner, by substituting for PRS, we will be getting the expression as sum over RS NR times e raised to minus alpha NR minus beta ES divided by, what do you get? That is sum over RS e raised to minus alpha NR minus beta ES. So that gives you the average number of particles. We need these two expressions when you discuss the energy and number fluctuations in grand canonical ensemble later. Okay, so these two equations are relevant for us. Let me call this one as equation number some 11 and equation number 12 to do with. Okay, so now before we end up this particular session, I think you remember the quantity that we have written here as the denominator, this denominator quantity. The denominator of the Gibbs distribution equation is what is known as what? It is a normalization factor in the probability. This is what is known as what we have named earlier as the grand canonical partition function, which we denoted by Z. Okay, so PRS is equal to, we can say, e raised to minus alpha NR minus beta ES divided by Z, where Z is sum over all states. Okay, sum over all states. Z stands somewhere, you remember that is a general term used for Z, the canonical partition function, whose relevance was discussed in the earlier topic, you know, because that acts as the bridge to thermodynamics of the system. Now, we will recall from our previous experience that we will be able to show that equation number 11, you see, equation number 11, by using grand partition function, I can write 11 can be written as average energy is equal to, that is E bar is equal to minus dou by dou beta of log of Z. Okay, I think you are able to understand how that comes, because, you know, let's take and see how it comes. You can just see that when you take log of Z, the derivative, what will happen? It will be, see, I'm writing it, this is equal to, let's prove it. Try to prove it. We will try to prove it. That is minus dou by dou beta of log of, what is Z? Z is sum over RS e raised to minus alpha NR minus beta ES. Okay, so this is the thing. So let's see what you're going to get. So, you know, dou by dou beta of log of something. What is log of derivative of log? That will be equal to 1 divided by that quantity. That is 1 divided by sum over RS e raised to minus alpha NR minus beta ES into multiplied by then dou by dou beta of, so there is a negative sign, of course, dou by dou beta of minus, let me put it, dou by dou beta of this exponential. What will be that one? So that will be the same exponential factor that is getting what? Repeated. Multiplied by, then then you have to take the dou by dou beta of beta ES, because alpha NR is a constant as far as beta is concerned. So that will be a minus beta will come up. So that will be minus ES will come out, minus ES into sum over of course RS, that is for exponential function, the same function will be getting repeated, minus alpha NR minus beta ES. Now just see what is this one. What is this one? That is that minus and minus will be getting plus, minus and minus will be getting plus. So what happens? Of course, this term has to be written first, or sum over RS should be written first here. So that will be nothing but sum over RS value ES into minus minus will become plus e raised to minus alpha NR minus beta ES divided by, can't you see what is there, this one? So this quantity is nothing but our Z itself, that is your Z itself, which is nothing but equation number, you can see that equation number 11 itself. Can't you see that? Equation number 11 itself. So we can say average energy can be written as minus dou by dou beta of log Z. Remember, in canonical ensemble, this was same thing. Okay, average energy in canonical ensemble. There was also we got, that is minus dou by dou beta of log of Q. We have proved Q and VT. Okay, so instead of Q and VT, we are using Z here. That's all in grand canonical ensemble. Similarly, we can write that from equation 12, by the same token, we can write that average number of particles, that is equal to n bar, that will be equal to what? Minus dou by, instead of dou by dou beta, here it will be minus dou by dou alpha, because alpha is the coefficient of nr, minus dou by dou alpha of log of z. So these are two equations which connects the average energy and the average number of particles in the grand canonical ensemble with what? Grand partition function. Okay, so that's about it. So we got the grand partition function, and from grand partition function, in the next lecture, we will be deriving the thermodynamics of the system in grand canonical ensemble, which is quite similar to that of canonical ensemble we have done using Qn as the canonical partition function. Okay, so please refer to canonical partition function and its thermodynamical derivations before you attend the next lecture. So it will give you clarity about the methodology that we are following in ensemble formalism, which is the same whether it is canonical ensemble or grand canonical ensemble, so that you will get an ease of what are the topics. Thank you.